lecture in Complexity in Materials Design. I'm Dave McDowell, Regents Professor and Carter N. Payton Jr. Distinguished Chair in Metals Processing at Georgia Tech in the Schools of Mechanical Engineering and Materials Science and Engineering. Learning outcomes of this module include a discussion of the traditional design iteration algorithm, why today's design environment demands concurrency of materials development. We'll introduce hierarchy of material structure and the role that this hierarchy plays in new methods for designing materials, and principles of robust materials design that are critical to mitigate uncertainty involved in systems engineering design of materials. So let's consider the traditional design iteration that involves rather limited iterations. This was largely before the era of high-performance computing, before the era of big data and the role of data science and informatics. We start with analysis feeding into design. You first analyze, you design, you prototype, then you realize products and you validate performance, scale up. There is limited amount of iteration that returns the design process back to the analysis stage, returns the prototyping back to the design. That kind of limited iterative traditional approach is giving way in the modern era to the role of modeling and simulation and data in high-performance computing. What does this enable us to do? We can now think about addressing material structure hierarchy. In the case shown here, we start with an aircraft at the top level and work our way backwards through the assemblies and sub-assemblies, parts and components. And traditional engineering design approaches have dealt with this top-down systems design approach for many years. Selecting materials, shown in the vertical black bar, to serve as input into the part design process. On the other hand, if we're designing the material at the same time as designing the overall structure or product, then we consider that we have to treat various scales of hierarchy or levels of hierarchy all the way from the individual atom layer and the structure of those atoms in a lattice through interfaces, the distribution of reinforcement phases through the lattice and individual grains, and through a polycrystal up to the part level. So the complexity here really lies in how do we make, how do we control these stages of hierarchy, these levels of hierarchy, and how do we understand the information associated with each level and how it contributes to the overall part design. So you see there's a shift to concurrent product, process, material system design from the classical paradigm of system design fed by material selection. So here we're interested in merging top-down system specification-driven design with bottom-up materials modeling, simulation, and experimental design. And necessarily, we need a lot of the bottom-up information to be achieved through high-throughput means, the basis of this course. This is a chart shown at lower left, a Venn diagram for the process structure property performance relations that was popularized by Professor Olson at Northwestern University, published in Science in 1997. It's driven much of the thinking of materials design. Foundational elements of systems-based materials design and development then include the use of mechanistic modeling, that is physically based modeling, and reduced order meta models or surrogate models that provide decision support for materials development. That is, what information is being developed or transferred from each level of hierarchy that informs the response of the material to deliver required capabilities to the part level. Necessarily, consideration of these different levels of hierarchy in space and time necessitate the introduction of robust design concepts, as well as multi-objective design methods, that is, multiple target material properties or responses. It's not enough to know, say, elastic stiffness or melting point. We have to have a lot more information, such as conductivity, strength, elastic stiffness, maybe fracture resistance, perhaps other properties, both physical and non-physical in character. This also introduces the need to manage complexity. when we introduce such complexity and such uncertainty, we have to manage that. And we do so by addressing the uncertainty, quantifying uncertainty, and by the use of distributed computing and e-collaborative networks between the large number of stakeholders involved in the process. If we break the Olson process structure property performance paradigm in a little bit more detail, we can see that we move from lower left to upper right through process structure and structure property mappings. These could be experimental or computational. Typically, they would need to be of high throughput character in the design concept exploration stage, or so-called preliminary design stage. And then finally, the linkage between properties and performance is a material selection problem. The material selection problem, as shown at lower right, is really the tip of the iceberg, the part that sticks out of the water, which is on the order of 10% of the overall mass of the iceberg. Hidden beneath the surface is the complexity of the process structure property relations that are dependent upon how we identify and model, whether it be through experimental interpretation or computational modeling and simulation, the relationship between structure and responses. So this brings to the fore the notion of how do we make decisions in developing and designing materials. Well, there are certain important elements. First of all, the acceleration of the discovery, development, and insertion of materials is fundamentally a decision-making endeavor. It's not a mathematical operation, it's not a computational operation. It is a decision-making endeavor. This is done by distributed teams of individuals at different levels of decision authority. And the aim is really to increase the fraction of important decisions that are informed by modeling and simulation, as well as being informed by high throughput experimental assays or methods that allow us to explore a wide range of options of material structure. Materials design and development is typically pursued in the context of product development. So the coupling with manufacturability is a natural one. And computationally assisted materials design and development involves decision support, not just model inputs and outputs. And this decision support is highly concerned with issues such as probability, reliability, uncertainty quantification and mitigation, and multi-objective optimization. These are fields that have at their core more strong relationship to multidisciplinary design optimization, systems engineering, elements that are beyond the typical reach of materials science, chemistry, and physics, but need to be incorporated in the vision of accelerating the design and development of materials. So a systems perspective is necessary. Thank you.